Okay, everyone. So let us move ahead of the last lecture, in which we had reached this point that we had got two equations to solve for planar waveguides. We had taken the waveguide as this diagram, that this is x-axis and this is, let's say, the z-axis, and we had assumed that there are two boundaries at distances minus d by 2 and x equal to d by 2. The refractive index between minus d by 2 to plus d by 2 is n1, and beyond that it is n2. And we showed that the electric field of any electromagnetic wave which would get caught inside this would be given by the solution of equation given by d2 Ey by dx2 is equal to kg square minus k naught square n square Ey. Okay, so this is also called secular equation or eigenvalue equation. Okay, so we had reached this point. So Ey is the solution of this, and n is n1 between these two boundaries, and beyond that it is n2. So for the region in which x is between minus d by 2 to plus d by 2, the equation would become basically d2 Ey by dx2. This can now be taken as complete differential also, because now it is a function of only x. So dx2 is equal to minus p square Ey, where kg square minus k naught square n1 square was taken as minus p square. And for the other two regions, that is when x is more than d by 2 or when x is less than minus d by 2, the equation becomes d2 Ey by dx2 is equal to q square Ey, where kg square minus k naught square n2 square is equal to q square. So the solution of these two, and these are simple equations that can be solved very easily. We can solve, let us say, the first one. Since you have a minus p square over here, so the solution would be of the form that Ey would be of the form e to the power plus minus I px. So the general form would be Ey equal to a e to the power I px plus b e to the power minus I px. Now, since this equation is symmetric in x, you can see that if you change x to minus x, nothing would change. N is also a function of x, but n1 and n2, from this diagram itself you can see that it is across, for x it is symmetric. So n1 and n2 also would not change when x is changed from x to minus x. So since this differential equation is symmetric in x, so the solution of that would be either symmetric or antisymmetric. This is the theorem of the solution of differential equations. So since the differential equation is symmetric, it can be shown, symmetric in x, so it can be shown that the solution Ey as a function of x would always be either symmetric or antisymmetric. So since we now have, this is a general solution, but looking at the requirement that this should also be symmetric, so for symmetric requirement, actually this would become symmetric if I take a and b same. So Ey is equal to a e to the power I px plus a here also, so a e to the power minus I px. Okay, now this becomes symmetric. So as soon as you put, otherwise if a and b were different, this could not have been become symmetric. So this is equal to 2a cos px. And for antisymmetric requirement, Ey would be equal to antisymmetric. This can be made antisymmetric if b is equal to minus a, which means that this a e to the power I px minus e to the power minus I px. So you can see that this is symmetric because Ey at minus x would become actually Ey at x. So this is symmetric choice. If you take a and b same, so this is Ey at minus x is equal to Ey at plus x, and this would become antisymmetric, which would mean basically that Ey at minus x would be minus of Ey at x. So it can be shown. So just by choosing b as minus a, which can be chosen because a and b are these are general and a b were arbitrary. So in the first case we chose a and b same. The second case we chose b equal to minus a. So this became antisymmetric. So this is nothing but 2ia and sine of px. Now this 2ia over here and 2a over here, since a is already constant to be determined, so arbitrary, so you can actually take these two solutions as we can say that symmetric solution is Ey equal to some 2a, I can write it as some a naught, let us say a naught cos px, or let me put these as a naught, b naught, a naught, a naught, a naught, a naught. So let me keep this as a only. So 2a naught is being kept as a, just for the sake of simple representation. So Ey is a cos px, and similarly for antisymmetric solution I can take Ey as some another b and sine px. Okay, so this equation, which had to have two kinds of solutions, symmetric and antisymmetric, and we saw that in the region when x is between d by 2 and minus d by 2, the solution would be, if it is symmetric, it would be of this kind, a cos px. If it is antisymmetric, it would be of kind b sine px. Okay, similarly we can do it for the other one, that is when so we take the case when x is greater than d by 2 and x is less than minus d by 2. So for these cases the equation is d2ey by dx2 is equal to q square ey, and the solution of this would be of the form e to the power qx only, and you could have plus minus, so e to the power plus minus qx, which means that the general solution, so this is in the region when x is greater than d by 2 and when x is less than minus d by 2. So Ey would be in general written as c e to the power plus qx plus d e to the power minus qx. Now if you look at the situation, if I choose the region when x is greater than d by 2, so x greater than d by 2 until infinity, less than infinity and d by 2. So you can see that if you take x very large, then this expression is such that this term is going to blow up. So which would mean that the electromagnetic wave will have infinite amplitude and infinite intensity. So that is not physically acceptable, which means that since c and d are arbitrary constants, so in order to keep our physical requirement acceptable, we must take c equal to 0. There is no other choice, because whatever, if you keep c over here, this term is going to blow up when x is very, very large. This is not going to blow up, this would go to 0. So this is acceptable. So c will have to be taken as 0, and Ey would be equal to d e to the power minus qx. Similarly, when x is less than minus d by 2 and greater than minus infinity, so when x is very, very small, minus infinity, you can see that the same equation, this would get blown up, but this would not. This would behave on, this would go to 0 when x goes to minus infinity. So in this region, you'll have to take d equal to 0 and Ey as equal to c e to the power qx. Okay, so now we can write the two solutions, that is symmetric and antisymmetric solution. Symmetric solution, we saw that there are three regions now. X, which is less than minus d by 2, then x, which is between minus d by 2 and plus d by 2, and then x, which is greater than d by 2. Okay, so these are the three regions. In this region, x less than minus d by 2, now we know that x less than minus d by 2 is this form. So it is Ey equal to c e to the power qx. For this, we have already shown that in this region, Ey would be equal to, so this is symmetric, so a cos px. And in this region, so this is this one, so Ey would be equal to d e to the power minus qx. But since we know that we have a requirement of being symmetric also, and the symmetric requirement would demand that actually this d should be equal to c over here, and unless until you put these two same, it would not be symmetric. So in order to, and this is our requirement, we must have a symmetric solution or an antisymmetric solution. For symmetric requirement, the c on both these must be same, so c e to the power minus qx. So this is our symmetric solution. And the antisymmetric, for antisymmetric solution, again the three regions, minus d by 2, less than minus d by 2, then x greater than minus d by 2 but less than d by 2, and then x greater than d by 2. So in these three regions, again you have the same thing, Ey equal to c e to the power qx. Ey here would be equal to b and sine px, that we had already derived that. And in this region, Ey would be equal to, now it is d e to the power minus qx, but in order to maintain the antisymmetricity, this would remain antisymmetric only if I choose d as minus c. For antisymmetric requirement, we have chosen d as minus c, and for symmetric requirement we have chosen d as c. This is necessary if you want the solution as symmetric, and this is necessary if you want the solution as antisymmetric. So these are two solutions of the equation that we had derived for the planar waveguide. Now there is another requirement of this, and it is that the for any boundary which differentiates two media of different optical properties, then we have already shown that the electric field and the magnetic field, which are parallel to the boundaries, would be actually same of the same value. They are continuous across the boundaries, whether it is this boundary or that boundary. So now we know that this is what we have been solving is a TE mode problem, transverse electric mode, and in that we know that only EY is not 0, HX is not 0, and HZ is not 0. Only these three are not 0, otherwise others are 0. So EY is which? EY is in this direction, perpendicular to the XZ plane, which would be parallel to the boundary. So EY is parallel to the boundary. HX is in the X direction. It would not be parallel, it would be actually perpendicular to the boundary. So it would not be continuous across the boundary. But HZ again is in this direction, which is again parallel to the boundary. So which means that EY and HZ, they are parallel to the boundary, and that is why they must be continuous across the boundary. So with these, on both these solutions, there is an additional requirement, boundary condition, and the boundary condition is that EY and HZ must be continuous across the boundary. So which means that it should be continuous at x equal to d by 2 also, and at x equal to minus d by. These are the two boundaries that we have in this problem. So EY and HZ must be continuous across it. And the expression for HZ, if you remember, we had already shown HZ. HZ is related to EY by dx. Apart from this, there's a constant factor. So if HZ is continuous, then dEY by dx would also be continuous, which means that instead of saying that EY and HZ should be continuous, we can also say that actually EY and dEY by dx must be continuous. Okay, so let us impose this so that we can get the values of A, B, C also, and then we'll have the complete knowledge of the solution of EY. We have already some knowledge about KG, and we will explore that further, but let us solve this. So the requirement of boundary condition, if you want to fulfill that, so let me take the symmetric case first. It's a symmetric solution, and the boundary is, let's say, x equal to d by 2. So x equal to d by 2, you have actually these two functions. This is between minus d by 2 to plus d by 2, and this is d by 2 and more than that. So these two must be same at d by 2, which means basically that EY at x equal to d by 2 must be same across in this also and in this also. So if I put d by 2 over here, EY at x equal to d by 2 is equal to, in this case it would be A cos P d by 2, and here it would be C e to the power minus Q d by 2. So this is for EY, and if I take dEY by dx at x equal to d by 2 in both the cases, both the cases. Then what would happen if I differentiate this and then put x equal to d by 2? So it would be cos px would become sine minus a p sine p d by 2 is equal to, and then differentiate this also, minus c q e to the power minus q d by 2. So these two boundary conditions gives us these two equation, and if I do this divided by this, then you can see that first we just remove this minus from both the sides. So you can see that this a would get cancelled, c would get cancelled, and you'll be left with p sine by cos is tan p d by 2, which is equal to c cancels and q only. So we get this condition. This for symmetric. If you would see that even at x equal to minus d by 2, it would be same as this equation. And let's take the another one, antisymmetric case. So for antisymmetric solution, you have these two equations, these three equations. Now again, when you would put the condition that ey at x equal to d by 2 must be continuous, then here it would be b sine p d by 2, and this should be equal to minus c e to the power minus q d by 2. And when you would impose dy by dx at x equal to d by 2 to be continuous, then differentiating this would basically mean that b p sine p cos sine would become cos p d by 2 is equal to, and differentiating this minus would become plus, so c q e to the power minus q d by 2. And now if I do this divided by that, b cancels, p would remain, cos by sine is cot p d by 2, and this is equal to minus q. Okay, we have got these two as our solutions, these two conditions. For symmetric solution we have this solution, this condition, and for antisymmetric solution we have this condition. If I multiply, or let's say divide the two, tan divided by this, then you can see that pp would cancel, tan by cot would become tan square. So tan square p d by 2 would be equal to q would also cancel, and we'll have minus 1. So tan square p d by 2 is equal to minus 1, which means that tan p d by 2 would be complex and imaginary. Tan p d by 2 is becoming I. Now this is impossible. This is impossible. So where did we go wrong? We have not gone wrong. Actually, the thing is that the solution would be either symmetric or it would be antisymmetric. You cannot, this equation is taking both of them correct simultaneously, which is not possible. It would be either this or this. Both simultaneously cannot be observed. So what do we get from these two equations? So if I take the first one, and what I do is I multiply d by 2 both the sides. So p d by 2 tan p d by 2 is equal to q d by 2. Okay, so this is for symmetric, and for antisymmetric Okay, so let me take this as alpha. So alpha tan alpha is equal to beta. I am taking alpha to be p d by 2 and beta to be q d by 2. So one is this. The other is for antisymmetric. Again we multiply d by 2, so p d by 2 cot of p d by 2 is equal to minus q of q d by 2. So this is nothing but alpha cot alpha is equal to minus beta. So these are the two, the new form of the same equation. Initially it was in p and q with d. Now we have chosen alpha and beta as our parameters and we have defined like that. We can also see that if you take alpha square plus beta square, alpha square plus beta square would be equal to, now alpha square is how much? Alpha square is p square, alpha is p d by 2, so p square d square by 4 plus beta is so q square d square by 4. So which means that d square by 4 can be taken common and you'll have p square plus q square. But if you remember the definitions of p square and q square, then p square d square by 4, p square is nothing but k naught square n1 square minus kg square, this is p square, and plus q square is kg square minus k naught square n2 square. So kg square gets cancelled and you get the expression of alpha square plus beta square as alpha square plus beta square becomes d square by 4 into k naught square n1 square minus k naught square n2 square, k naught square n2 square. So d square by 4, you can take even k naught square out, so n1 square minus n2 square. So this is our alpha square plus beta square. So this would be true always because we have taken alpha square and beta square according to the definition. So alpha square plus beta square would be equal to this much always. I can write this as some r square, where r is equal to d square root of this. So d by 2 k naught into n1 square minus n2 square under root. So r is this much. Okay. So this is the equation that alpha and beta would always satisfy, and along with that you have if the solution is symmetric, the condition would be that alpha tan alpha would be equal to beta, and if it is antisymmetric it would be alpha cot alpha would be equal to minus beta. So this is for symmetric and this is for antisymmetric. So how to get these solutions? So we get the solution graphically. What we do is we plot this side, we plot alpha, and this side we plot beta. So alpha is alpha, beta would be, for symmetric, beta would be alpha tan alpha, and for antisymmetric, beta would be minus alpha cot alpha. Okay, for symmetric, beta is nothing but alpha tan alpha, and for antisymmetric, beta is equal to minus alpha cot alpha. So let us draw this. So alpha tan alpha. So how the tan alpha would vary. Okay, and alpha and beta, according to our definition, alpha and beta are all positive numbers, positive quantities. So we'll plot the curve only within this quadrant when alpha and beta are positive. You know that tan pi by 2 is infinite. So alpha tan alpha, so if I'm plotting this for symmetric, alpha tan alpha, then at pi by 2, at alpha equal to 0, it should be 0. So it is 0 over here, but at alpha equal to pi by 2, this should go to infinity. This should go to infinity, like this. Again, the same starts from minus infinity. It would come to 0 at pi, and when it becomes 3 pi by 2, it would again become infinite. So the curve would be like this. Again at 2 pi it would be 0, and at 5 pi by 2 again it would be infinite. So the curve would be like this. So all these lines that we have drawn are the curve for beta equal to alpha tan alpha. Okay, all the three lines that we have drawn. Now let me plot this one, minus alpha cot alpha. Now cot alpha and tan alpha are inversely related, which means, and there is a minus sign also. I have plotted for tan alpha, but it hardly changes its behavior even if you multiply by alpha, because infinity would remain infinity and 0 would remain 0. Okay, so it hardly changes the nature of the curve, whether you take tan alpha. So we have more or less plotted tan alpha, but the behavior would remain same for alpha tan alpha also. Similarly for this one, alpha cot alpha, so behavior of minus cot alpha, you would see that actually those curves would be drawn like this. It would now go to plus infinity. At pi it would come to 0 when tan is infinity, cot would be 0. When tan is infinity, cot would be 0. And so the curves will be like this. So the dashed curves are for antisymmetric, dashed curve antisymmetric, and the solid curves are for symmetric. So these are, I have drawn alpha tan alpha equal to beta, and I have drawn alpha cot alpha equal to minus beta also. But alpha square plus beta square, now this is a constant for a particular case, because d is the distance between the two boundaries. n1 and n2 are the two refractive indices, n2 square, and k naught is nothing but the wave number of vacuum of the electromagnetic wave, omega by c basically. So this whole thing will have a constant value, and alpha square plus beta square equal to r square is nothing but an, on this graph, when you are plotting alpha this side or beta this side, so on this graph if you try to plot this, it would be nothing but a circle. So a circle would be drawn like this. Okay, so this is the circle. Alpha tan alpha are the the solid line, and the dashed lines are for antisymmetric. And so wherever these two lines cut, so at this point there would be a solution, at this point also there would be a solution. So these two would be symmetric solutions, and here you'll have antisymmetric solution. So this is antisymmetric solution, and these two would be symmetric solution. Symmetric solution and antisymmetric solution basically mean that there would be a value of alpha that would satisfy this equation and this also. So alpha value at this point, alpha value at this point, alpha value at this point, they would satisfy the whole condition, all the condition. Alpha at this point, alpha at that point would give you symmetric solution, but alpha at this point would give you antisymmetric solution. And you must remember what is alpha. Alpha is P d by 2, and P is nothing but k naught square n1 square minus kg square under root d by 2. Okay, so you can see that a value of alpha that would correspond to this, let us say this solution, would actually give you a value of kg, because all others are constant. So alpha, if alpha has a value, n1, k naught, d, all they are already having some value. So alpha square, alpha would actually fix the value of kg. So one particular intersection would give you a value of kg. So this will have a particular value of kg, this will have a particular value of kg, this will have another particular value. So each intersection has this kg1, kg2, kg3. So the equation that we had started with, now we can see that we have got the EY also, and we are getting kgs also as solution, but kgs are not not a single value solution. You have many values of kgs as solution, and it will also depend upon the radius of this circle. So r, the value of r would determine that how many solutions would exist, because if you can see a greater value of r would cut these lines at many other points also. Okay, so if r, you can see now that if r happens to be less than pi by 2, because this is r, this r is actually this much. So if r happens to be less than pi by 2, it would only cut this line and no other lines. So if r is less than pi by 2, one symmetric solution. If r is between pi and pi by 2, between pi, less than pi but more than pi by 2, then you will have one this and the other this. So one symmetric and one antisymmetric solution. Okay, so similarly you can work it out and see that r, if r happens to be less than, this is 2 pi by 2 and this is 1 pi by 2. Okay, so if it is n pi by 2 and n minus 1 pi by 2, so between these two, so 2 means you have, if n is even, if n is even, so it would work like this. So you'll have two solutions, the even solutions. So n just as 2 over here, so 1 this and 1 this. So it means that n even solution would basically mean that equal number of symmetric solution, equal number of antisymmetric solution would be there. So if it is less than pi, you have one symmetric and one antisymmetric. If it is less than 2 pi, less than 2 pi, then 2 antisymmetric and 2 symmetric solution. If it is less than 3 pi, then you'll have 3 symmetric and 3 antisymmetric and so on. Okay, so n would actually give us that how many symmetric solutions. You can actually work it out and see that how many solutions would exist depending upon what is the value of r. R is between what and what. So if it is less than 3 pi by 2, it will have 2 symmetric solution, 1 antisymmetric solution. If it is 3, 2 and 2. If it is 2, then 1 and 1. Okay. If it is 4, 2 pi, then 2 and 2, and so on. So n would actually decide that if n is even, then n by 2 symmetric and n by 2 antisymmetric. And if n is odd, then n plus 1 by 2 symmetric and n minus 1 by 2 antisymmetric. Okay, so R between this actually would decide that how many symmetric solution and how many antisymmetric solution would be. You must remember that each solution would actually specify one value of kg for itself. Okay, so if you talk of let's say the solution, and as we had started with, in Ey as a function of x is E0 y, x and t. The solution is Ey as a function of x and t is equal to E0 y as a function of x into e to the power I omega t minus kg z was the solution that we had started with. So our problem was to find out E0 yx and kg. E0 yx, now we see that we have actually two kinds of solution. So E0 yx is something that we were determining it as Eyx, it's the same, and we had solution as symmetric and antisymmetric. So Eyx minus t by 2 x minus t by 2 plus t by 2 and x greater than d by 2 has that sort of solution. Ey is equal to, we have already shown those things, and it is this. So Ey, this is E0 y basically. So this is the symmetric solution, this is antisymmetric solution, and kg, now we know that kg would be given by values that would satisfy at the intersection. So which means that all values of kg is not possible. There would be only certain values of kg which would be accepted as the solution, and it would depend basically on the problem that what is the value of r. So d, n1, n2 and k0 would decide what is r, and r would decide that how many values of kg would be possible, and kg would tell us that which one would be symmetric solution, which would be antisymmetric solution, and E0 y would be actually for symmetric E0 y would be taken as symmetric wala, and for antisymmetric it would be taken as this. So this is how we have solved the planar waveguide problem. In the next lecture we would just summarize this whole thing and try to understand that what do we mean by having different certain values of kg as solution. So what do we in terms of the waveguide, what would that give us, and we would see basically that different values of kg would actually tell us that the direction of the accepted electromagnetic waves would be only chosen in some angles only. 1 kg would decide one single direction of the electromagnetic wave. So all it appears as if that you can throw the electromagnetic waves in any direction as long as the angle is more than the critical angle. But this actually tells us that all the angles are not physically possible. There will be only some selected values of kgs, and kgs, the selected values would be decided by the intersection of the graph that we have shown. So from there we would get the selected value, and those values would actually give us the direction of the electromagnetic wave that would get trapped inside the. So all these we will discuss in another lecture. Thank you very much.